Good morning, students. So we will discuss about Noether's theorem. So which was introduced by Noether from German, Jew, a very famous mathematician and theoretician. She lived in around 1930s. Well known for abstract algebra, Noether's theorem, and all those things. Noether's theorem is very famous for symmetries and conservation laws. So whenever you find some symmetries in physics, in nature, you can find some conservation will exist. Of course, we know about the conservation of energy, we know already. When you take any trajectory path of particle, wherever you find the energy will be the same. The total energy will be the same. Of course, there will be variation of kinetic energy and potential energy, but put together, the energy is conserved. So we know already about conservation. And symmetries. So symmetries are very important in physics. For example, when you just have a charge. So you are going to keep a positive charge, the lines are coming out. So we know already. If I am going to measure the electric field here, I will get some value. If I am going to measure the same radius of curvature, if I am going to measure here also, I will get the same value. Wherever I go with the same curvature, I will get the same value. So this is exactly resembles with a symmetry, so space symmetry. For example, I am going to measure acceleration due to gravity using simple pendulum today, now. And maybe in the evening I am going to measure again. With the same environment, I am going to measure again. Maybe tomorrow I am going to measure again acceleration due to gravity in some other lab with the same environment. Again the answer is the same. The answers will be the same. So what we say this as time symmetry. So whenever there exists symmetry, and surely there will be conservation of energy. So both go hand in hand. So for example, we take angular momentum. So again conserved one. So symmetry is there is a relationship between symmetry and conservation. And here also we are going to discuss about the current vector. So already we discussed about the current vector earlier with having 4 coordinates x, y, z and ICT. So we know already about the time coordinates and space coordinates. We are going to look into the same aspect about symmetry and conservation of energy. Okay, and not only in physics, not only in quantum mechanics, but also in many other areas, like for example Newton's 3 laws. Symmetry and conservation exists. And what of the E equal to mc squared, the relation between matter and energy, again conservation and symmetry exists. She could explain clearly everything about conservation and symmetries. So now we will discuss about Noether's theorem. So Noether's theorem, named after mathematician and theoretician Noether from Germany, illustrates the fundamental concepts of quantum mechanics. Noether's theorem explains the 3 fundamental laws of motion, Newton's laws of motion. Noether's theorem demonstrates the relation between energy and matter, E equal to mc squared. Noether's theorem illustrates an intrinsic link between symmetries and conservation of laws. This is the base. So there exists the hand-in-hand relationship between symmetries and conservation of energy. A symmetry is anything in which you have some sort of object and some sort of transformation. So when you are going to transform, the result must be the same. Okay. So we say that a system has a symmetry under a transform if the total energy of the objects will not change. So will not change. For example, time symmetry, translation symmetry, rotational symmetry. So symmetries are going on. Okay. Noether's theorem asserts that to each continuous symmetry, there corresponds a current, which we are going to discuss now, which satisfies the continuity equation. So it has to satisfy the continuity equation. Or equivalently, a quantity which is conserved. Continuity equation mainly deals about the conservation. Here we are going to discuss about this equation. So this is the equation that we are going to end up with, and J stands for current density. Okay, which is related with the current charges. The movement of charges will give us current. Okay. So every continuous symmetry of the Lagrangian gives rise to a conserved current, which is denoted by this symbol, such that the equation of motion implies us. So this is nothing but the equation of motion. We are going to use equation of continuity and conservation law. Symmetries and their conserved currents are incredibly important in the field theory, and hence Noether's theorem is an invaluable tool for the field theoreticians. So we know that action in classical mechanics is a function of field and its derivative, and it satisfies the field equation. So we know already this L, which is a function of L bar, Lagrangian density, which is a function of psi, del psi dot, and t. So they are all derivatives. So they are satisfied with the field equation, which is the equation of motion of fields with the following form. So we know that Euler Lagrangian equation is given by this equation if in the absence of time. Of course, Lagrangian equation, we know that there will be 3 terms, correct? 3 terms. So now I am going to leave the time factor for the time being. So we will have this expression as Euler Lagrangian equation. The above equation is obtained by varying the action using Hamiltonian variation principle. So above equation is obtained. Let us consider an infinitesimal transformation of the field. Now you are going to consider the transform. So psi becomes psi plus del psi. Accordingly, we see that these will be completely unaffected for any transformation which takes a form as exactly. So Lagrangian also will have infinitesimal transformation, and similarly Lagrangian density also. So if it is so, psi equals psi plus del psi, then your Lagrangian density will become Lagrangian density plus df mu by dx, partial df mu by dx. And we are going to replace this partial d by dx is nothing but d mu. Okay, where mu stands for covariant vector. We know already 1, 2, 3, 4. Here for the time being we have written as x. Okay, so d by dx, partial d by dx is replaced by d mu. Okay, partial d mu. So this Lagrangian density is written exactly like this. So where f mu is some function of the field that we are going to discuss about the current vector, some function of the field f of psi. If it is so, then the equation of motion, equation 10.46 remains unchanged. Okay, 10.46 remains unchanged. It is a symmetry if the Lagrangian changes by a total derivative, del psi dot, total derivative. This gives a change in the action of the general form as. So we know that Lagrangian density depends on psi comma del psi. For the time being, it have psi comma del psi. Then we will have to use partial differentiation rule. So which goes with exactly like this. So you have partial d L bar by first one. Okay, partial d psi del psi plus the second one is del psi is nothing but psi dot. So we can write this as partial dl by partial d psi dot del psi dot. Is it okay? Your psi dot is d psi by dx. Okay, it is not d psi by dt. It is d psi by dx and d psi by dy, d psi by dz. So equation 10.50. So this equation can be written as exactly like this. How to write this one? Del psi dot can be written as del psi dot is nothing but d psi by dx. So d by dx, partial d by dx can be replaced with d mu. So d mu del psi. So we are going to replace this term as this term. Okay. Similarly, partial d psi dot can be written as partial d psi dot is nothing but d psi by dx. So this can be written as d mu psi. So this term is replaced with this d mu psi. Other terms are let it be like this. Any doubt? Equation 10.51. So now, I have written the same equation. The first term of equation 10.51, just take the 5.1, satisfy the equation of motion, hence 10.46 as the first term represents the equation of motion. Okay, now we will go for the second term. Just we can write the second term. So here del L equals this equation can be replaced with using Lagrangian equation. This is Euler's Lagrangian equation. So del partial dl by d psi can be replaced with this expression. So we are going to replace del L by d psi as this term. Second term, let it be like this. I repeat, see here, partial del L by del psi can be replaced with this expression. This expression is nothing but the equation of motion, field equation of motion, Euler's Lagrangian equation. So instead of this, you are going to write this expression. So we have written this expression. And also here, partial d by dx replaced by d mu. So d mu. Now we know that product rule says product rule. So product rule is nothing but part d u b is nothing but u dv plus v du. We know already. So now you are going to differentiate this, keeping this as constant, plus you are going to differentiate this, keeping this as constant. You will get this expression. See here, you are going to differentiate this. So we have differentiated, keeping this as constant. You are going to keep this as constant. You are going to differentiate this. So we have differentiated. So these two terms can be replaced with 10.53 equation. Is it okay? So now if this transformation is a symmetry of the system, also we can have del L equals d mu f mu. Suppose if it is true, then we can write this expression d mu f mu. So using equation 10.53 and 10.54. So we have 10.53 is here, 10.54 is here. Okay, this is the expression that we have obtained. This is the expression from 10.53. You compare these two, we will have d mu f mu is given by this expression. Taking common terms out. Common terms nothing but partial d mu. The remaining term we can write this as exactly like this. See? You bring this term to that side, common terms, take the common terms out, you will have this expression. Now the argument is nothing but either this term can be equal to 0 or this term can be equal to 0. So argument. So this term d mu cannot be equal to 0. Only thing is this can be equal to 0. Whenever there is a continuous symmetry associated with the Lagrangian, then this quantity will be equal to 0. So this quantity equal to 0. So this is termed as this is termed as j mu. So partial d mu j mu, which is equal to 0. Okay. So this is what we are going to term this as j mu, current density, and remaining one is partial d mu. So partial d mu j mu, which is equal to 0. Is it okay? So associated to every continuous symmetry, we have a conserved current. So it represents as conserved current. What does it mean? J mu equals constant. Okay, it represents J mu is a constant value. So it means that we have a conserved current. So this is our conserved current. So thus we have proved Noether's theorem. So this is a stronger result saying we get a conserved charge. Indeed, a conserved current gives rise to conserved charge. So whenever charge moves, there will be a current. So here we have always we are talking about conserved current density. So conserved current density that we have obtained using this equation, which says that the Noether's theorem is proved. Okay. So we'll stop today, students. We will see in the next class. Bye, students.